All right, a new but similar approach to finding volumes of rotation, this time thinking about it differently in terms of cylinders and rings. So just a review of our story so far. We have found volumes of cylindrical shapes by thinking about the area of the parallel surface to the base and then pushing it down like a piston to fill out a volume. So we get the volume there by the area times the height. Well, with cylinders and rings, think about, with this new approach where we're talking not about discs but about cylinders, think about this same shape as being like a sponge, and what we're going to do is we're going to take and look at an outer ring and then we're going to contract it like squeezing a sponge until it's just a line in the middle. All right? So to do that, we have to think about, well, what is that ring around the outside? That's, if we open it up, it would be a surface like this that would have a circumference and then also a height. There's our height and there's our radius. Right? Now we've got our radius and our height, but we've opened up this outer ring, and there's our circumference, that's still the height. Well, that distance there is going to be 2 times pi times the radius of a circumference. And what we're going to do is we're going to let that ring contract and basically squeeze out the volume. So to do that, we're going to integrate from 0 to r, and as that contracts, we're going to write an equation that will mimic this area. And just like in this case, when an area moves a distance, we get a volume. Here, when this area shrinks into the center, we get a volume. So it's going to be the circumference 2 pi r, and then times the height, and then we're going to let that shrinking happen by changing r, shrinking it little by little by little by little. And think about our volume as being defined this way. Okay? So in this particular case, we would then integrate from 0 to r, 2 pi r times h, and then think of it as like, in this case, dx, all right? Because we could think of this as being oriented on a xy plane. Well, if we do that, 2 pi and h are just constants, so that could come out. 2 pi h comes out, left with 0 to r, r dx, in which case now our radius is, if it's oriented in the x dimension, will just be x. I should have written it like that. Okay. Well, if we integrate x, we get then 2 pi h, then times 1/2 x squared from 0 to r. Integrating x gives us 1/2 x squared. Well, that's just going to give us then 2 pi h times 1/2. When we put in r, we get r squared. We put in 0, it all goes away, so we've just got this. So that's going to give me 2 times 1/2 will cancel. I get pi r squared h, which is exactly the same volume formula that we'd expect if we did it this way, where we found the area of the circle and then moved it a distance h. That would also be equal to pi r squared h. All right, well, what does that mean in practical terms? Let's do a really simple example. Let's say we've got the same volume that we did before. It's simple parabola. It's going from 0 to 2, and it's y equals x squared. But we're going to do this, and we're rotating it around the x-axis. Okay, so it's a little bit awkward that way because we're going to do this in terms of y, but we haven't done an example like that. So it's this shape that's spun around this way. And so we're going to make these rings. Well, really, when we integrate, in this case, we're going to go from 0 up, in this case, to 4. We're going to let these rings start here in the center and move out. So I'm going to draw like a typical ring like this that's moving in that direction. There's our ring. So to do this integration, we're going to integrate in terms of y from 0 up to 4. So we're moving this way. it's going to be 2 pi, and then our r, our radius, is going to be our y value, and then we are going to multiply that times the height of this. What is the height of this ring as it moves out? Well, it's always going to be fixed at the top by 2, and then at the bottom by whatever this is. Well, I need to solve my original equation, y equals x squared, to make it x in terms of y, so it's radical y. So it's 2 minus radical y, and then dy is our variable of integration. So think about that again just to review. It's going to always be the circumference, 2 pi r. In this case, we're letting this variable, as our ring moves away from our axis of rotation, it's in the y orientation, so it's 2 pi y. Then how tall is that? It's going to be this distance 2 minus the function that gives us that curve, which is radical y. So all I need to do is perform this integration. Just try to do it quickly. This gets tedious at times, but I bring the 2 pi out, and it's from 0 to 4. If I multiply that in, it's 2y minus, and I'm going to get it out of radical notation, y to the 3/2, and then dy. What does that equal to? That's 2 pi times integrating, it's giving me y squared minus, and then add that up a notch, so it's 5/2, and that means it's 2/5, and then I'm integrating from 0 to 4. So if I do this, I'm going to plug in 4, and I get 2 pi times 16 minus 2/5 of, plug in 4, take the square root, that gives me 2, raise 2 to the 5th, it's 32. And let's just quickly grind this out. 2 pi times 16 minus, well, that's 64/5. 64/5. 5 goes into 60, 12, and 4/5 left over from the 4 from 64. And then if I do this math, that is going to be 3 1/5 times 2. That's 6 2/5 pi. 6 2/5 pi, which I think if we go back to our last episode, that was 32 pi over 5. So these guys agree. We found the volume 2 different ways. You can compare those two. All right. So similar problem, but different would be maybe one that is integrating a shape that might be, let's say, I think this is similar to one of your homework problems. If we have y equals e to the x squared, all right? So that is zooming way up steeply, okay? And let's just do it from 0 to 1, all right? And we're going to do this, let's rotate this around the y-axis here. So this is going to spin around and make like a bowl shape as our volume, all right? I won't attempt to draw that, but the volume then will be, if I sketch in like a representative disk like the books ask you to do, I'm going out a distance x there, and I have a height that's this value here. So it's pretty simple to write. I'm going from 0 to 1, and it is, bring the 2 pi out front from the very beginning, and then it's x is the radius times that height, e to the x squared, and then dx. Okay, so we have to integrate that. Well, this should look maybe a little bit familiar, I think, from one of our homework problems way back in the last chapter. How do we integrate this? This is one where we need to do it by parts. So using our Lie8 rule, this is the exponential. Oh, actually, no, we can do this with a simple substitution. There's x and there's x squared. So if I just simply let it be u equals x squared, then du is equal to 2x dx, and 1/2 du is equal to x dx. So that means this can be written as 2 pi times the integral. So if I plug in 0, I get 0. If I plug in 1, I get 1. So that makes that easy. And then it's e to the u, and then du. And then I'm going to pull out 1/2 because it's 1/2 du. So I get then pi with the 1/2 times the 2. And to integrate e to the u is pretty simple. That's just e to the u. And I'm evaluating that then from 0 to 1. Well, piece of cake for this then, because it's just going to be equal to pi, and that's going to be times e minus 1. All right? So that would be the volume of that shape. And of course, I've left off any talk of units. That's kind of bad form, I think. It's always going to be units to the third, and I think just for the sake of simplicity and all that, we will skip using units because it can be understood and implied. All right, then as a final closing thing, I did one of the problems we'd done earlier. This was the problem from last section in volumes of rotation, where we did this shape that was 1/4 x squared and 5 minus x squared, and it made this strange little like trumpet shape. Went through it all. I just abandoned it here because it looked like it was going to be just too awful. So while I was off camera, I solved it. You can look at the work there. It winds up being pi times 40 radical 5 minus 88 over 3. That's the exact answer. The radical 5 bits combine, and the thirds kind of canceled out a little bit, and got that. So now we can do this using our new technique, our cylinders method. So if you look here, this is the same shape, drawn it a little bit bigger. We're taking this shape here, and because we're spinning it around the x-axis, we can use the cylinder method in one go. We don't have to break it into two parts. Here's like a representative cylinder where, as this is my radius, that's y, moving out. It's going to go out to this point here, which is 2, 1. So that means I'm integrating here from 0 to 1. I have to just identify what is my upper curve. It's that one. And my lower curve is that one. So you can see I've just gone backwards, and I've solved each of these expressions that are functions y in terms of x to make them x in terms of y. Each of them just solved. And I wrote them. There's that upper curve, or outer. It's always the outer curve, and then the inner curve being subtracted away, and what's left over will be this volume. So you can just follow through the math. Again, it takes a lot of time to do this. To integrate here, I made a little substitution. I said let u be equal to 5 minus y, and so in place of the radical, I make it radical u, but then I had to, after doing du is equal to minus dy, I then also noted that y is equal to 5 minus u. So I put this in place of y, 5 minus u. In place of the radical, I replace that. This allows me to distribute that out and then do the integration. So again, this is why we spent the time learning those integration techniques. So I integrated here. I converted it back out of the u form. So even though I changed my parameters here, I went back and went through very carefully, and lo and behold, I got the exact same answer. So you can pause that if you really want to see. It's more the setting up that I'm interested in, and that should give you a couple of examples to help.